Hello everybody. My name is Lisandro Matters. I'm the head of sales and marketing at ENGYS. In today's webinar, I will talk about the new features and enhancements of Helix version 4. If you have any questions, you can use the Q&A feature to include your questions, and I will reply to them right after the webinar. Alternatively, you can always send an email to info@enggys.com. So, ENGYS generally releases 2 Helix versions per year. We have previously released 3 major Helix versions, each containing significant changes and feature enhancements to both Helix source code and Helix graphical user interface. With this recent release of Helix version 4, we are taking a major step forward in transforming Helix into a multi-physics solution system, which we call the Unified Solver Framework. This evolution represents a big consolidation and generalization of the CFD tools we offer. The refactoring of the code in this new version unlocks next-level capabilities. Even though previous versions of Helix contained numerous CFD solvers and models for a wide range of engineering applications, certain limitations prevented users from fully exploiting the available features. In this version, we focused on efficiency, consolidation, consistency, interoperability, and quality and maintenance of the code. The Unified Solver Framework contains solvers, models, and utilities in a modular fashion, enabling seamless communication and unlimited combinations of the physics that Helix is capable of. This game-changing update makes Helix a highly flexible and versatile CFD tool. With version 4, a series of enhancements were done to each aspect of Helix to deliver a more powerful and efficient user experience. The new features and improvements that have been introduced in Helix version 4 include improvements in our mesh algorithm, setup interface, solver, post-processing tools, and also in Helix additional modules. Let's see in more detail the enhancements in each aspect of Helix, starting with our mesh generator algorithm. With respect to mesh generation, Helix version 4 presents a noticeable overall enhancement of the extrude mesh algorithm's performance and accuracy. Our primary objective in this update has been to generate low Y+ meshes more effectively. These low Y+ meshes are crucial in accurately resolving boundary layer effects in CFD simulations. To achieve this, we've focused on generating high aspect ratio cells at the surface, which allows for better resolution of the flow near the walls. This improvement leads to more accurate simulations, especially for complex engineering applications. Furthermore, we have developed a robust methodology that ensures an error-free mesh is generated in a timely manner. This reduces the chances of encountering issues during this simulation process and allows you to focus on interpreting your results. We have also added a new face merge option within the extrude algorithm, which is applied before the layer addition step. This innovative feature allows you to reduce the overall cell count by approximately 10 to 40%. By reducing the cell count, you can achieve faster and more efficient simulations without compromising the accuracy of your results. As you can see in the 2 images displayed on the slide, the left image represents a mesh with the merge face option turned off, while the right image showcases the same mesh with the merge face option turned on. It is possible to note that the amount of cells displayed on the cylinder surface in the left image is higher than in the right image. With respect to near-wall layer controls, Helix version 4 provides users with greater control over near-wall layers. Now, users have the option to specify either the maximum layer thickness or the final layer thickness for their near-wall layers. This added flexibility ensures that you can create meshes that accurately capture boundary layer effects while adhering to your specific simulation requirements. Moreover, you can choose between absolute or relative sizes for the layer thickness, further expanding the customization options available to you when generating your meshes. The image on the slide demonstrates a mesh with a maximum layer thickness set to 10 millimeters, showcasing the level of control you can achieve with the new near-wall layer controls in Helix version 4. Generating high-quality meshes around sharp edges can be quite challenging. However, with the introduction of an extrusion step in the improved layer addition process, We have successfully addressed this issue, resulting in more accurate and error-free mesh generation around sharp edges. To provide even more control, we have added an additional keyword in the advanced options, allowing you to set the fan angle in degrees. This new option enables you to customize the mesh generation process further and achieve the desired level of precision for your specific simulations. Low Y+ meshes are crucial for accurately resolving boundary layer effects in CFD simulations. However, creating these meshes can sometimes lead to high warpage hex cells, which can negatively impact the accuracy of the simulation results. To address this issue, we have added a new option in the advanced layer options that allows you to significantly reduce warpage in your mesh. This innovative feature enables you to split high warpage hex cells into prisms, resulting in a more accurate and reliable mesh. 3 additional layer options were introduced in Helix version 4 to provide the user with greater control over the final mesh quality. First one, the Extrude Blend option. This new feature allows you to blend layer stacks from their surface, normal direction, to their outer layer stack position. By using the Extrude Blend option, you can create smoother transitions between different layers in your mesh, resulting in more accurate simulations and better overall mesh quality. Secondly, the layer matching option. With the layer matching option, you can increment or decrement the number of layers at the interface of lower and higher layer count patches. This feature helps ensure a consistent mesh across different regions, allowing for more accurate and stable simulations. And lastly, the new squish option. The new squish option enables you to disable layer projection at non-layer cells. This feature is particularly useful when dealing with complex geometries, as it prevents unwanted distortions in the mesh and ensures a more accurate representation of the geometry in your CFD simulations. With respect to the Extrude Mesh feature, we have a new option to extrude mesh regions based on 2 different criteria. The user can extrude the mesh based on source and target patches. This option allows you to specify the source and target patches for the extrusion process, providing more control over the mesh generation in specific regions of your model. Or by using a direction vector, in which the user can define a direction vector for the extrusion process, providing even more flexibility when generating your mesh. Lastly, the Extrude Mesh feature also supports zone creation, enabling the user to create cell zones from such mesh extrusion. In Helix version 4, a new tab named Transform was added to the Geometry data panel to allow the user to set up surface transformations that will be created during the meshing process. This allows users to set virtual transformations that are applied in sequential order to the geometry without changing the geometry itself. The following types of transformation are supported: translate, rotate, scale, and recess. Lastly, we have other mesh enhancements added to Helix, such as pre-visualization of the automatic base mesh in the display. This new feature allows you to preview the automatic base mesh directly in the display before finalizing the mesh generation process. By providing an early visualization, you can easily identify any potential issues or make adjustments as needed. Also, this version 4 now supports the export of mesh statistics in both XLS and CSV formats. This enhancement makes it easier for you to analyze and share your mesh statistics with colleagues, or integrate them into external tools for further analysis. And now, users can import geometry files in Nastron triangulated format. Now let's take a look at the enhancements applied to the setup step of Helix interface. As part of the Helix version 4 improvements, we have entirely refactored the material properties library, resulting in a more streamlined and flexible system for managing material properties variables such as viscosity, density, compressibility, and heat capacity. The new material properties library offers a simplified interface as it consolidates all material properties into a single file. This is a significant improvement compared to the previous library inherited from OpenFOAM, which used different interfaces depending on the selected solver. For instance, incompressible solvers required a transport properties file, while multi-phase compressible solvers used a thermophysical properties file. Additionally, other properties such as Lagrangian particles and radiation had their own separate interfaces. With Helix version 4, we've introduced a higher level of flexibility in specifying material properties variables. Users can now define how these variables are calculated independently. For example, you could choose to calculate density using a polynomial function, while viscosity is determined by the Sutherland model. This is a significant advancement from the previous Helix implementation, which offered a limited set of predefined combinations. Moreover, users can now define any material property variable to depend on any field, offering even greater customization options. In conclusion, the refactored material properties library in Helix version 4 provides a more streamlined and user-friendly interface, along with increased flexibility, enabling you to efficiently manage and customize material properties for your specific simulation needs. We also have a new interface for generic passive scalars, or tracers, as you can see in the image in the right. Any user-defined tracers can be saved in the Helix materials library. In Helix version 4, there is now support for multi-species mixtures, enabling the user to accurately simulate complex scenarios that involve various species. This enhanced support ensures more realistic and reliable simulations for a broader range of engineering applications. In the Helix version 4, material properties can now be derived from weighted mixture models. This improvement allows you to better represent the interactions between different species in your simulations. Also, the user can now define species properties for both boundary conditions and sources. This enhanced capability provides greater control, allowing the user to fine-tune the behavior of individual species within the CFD model. In the context of our universal single-phase solver, we've introduced an improved buoyancy algorithm. This new approach allows us to calculate pressure directly, making it much simpler to switch between buoyant and non-buoyant flows. This feature is particularly helpful when troubleshooting problematic cases or crashes, as it enables you to quickly determine if buoyancy is the root cause. The user can restart the simulation using the same solver for both scenarios by simply toggling buoyancy on or off. We have both variable density and Boussinesq models supported for buoyancy flows. As demonstrated in the images in the slide, we have compared our buoyancy algorithm to standard commercial CFD tools in the market, matching greatly accuracy, robustness, and stability. With respect to radiation features, introduced in Helix version 4, we have focused on the modeling of participating media. We have introduced two new volumetric radiation submodels for participating media. Constant absorption, which represents a simplified approach where the absorption coefficient is assumed to be constant throughout the participating medium. And soot radiation, whose submodel accounts for the effect of soot particles on radiation absorption and emission in the participating medium, providing a more accurate representation of the radiative heat transfer in combustion processes. To accurately simulate soot radiation, Helix requires the use of tracers, or a multi-species mixture model. This ensures that the soot particles and their interactions with the participating medium are properly accounted for in your simulations. A new method for defining local coordinate systems and body motion has been added with reference frames. Reference frames can be defined relative to the global coordinate system or nested in other frames. For example, a wheel frame can be nested in a vehicle frame to accommodate the motion of the vehicle. These frames can be used with sources, boundary conditions, monitoring functions, and dynamic mesh motion. All velocity boundary conditions now have reference frame functionality. This means boundary velocities are added to the velocity of the reference frame attached to it. The absolute velocity applied at the boundary will be the local relative velocity of the boundary, plus the velocity of the reference frame and all its parent frames. This specific type of boundary condition allows users to map the value of a field, such as velocity, temperature, or turbulence, from a source patch to a target patch. This is useful in cases where the boundary condition at the target patch is directly influenced by the field values at the source patch. The user can now import data from a CSV file, and also can make use of the local reference frame applied, either Cartesian or cylindrical. We have added a new flow rate target outlet boundary condition, whereby the user can specify the target outflow flux on a patch. 3 different options are available to the user for specification: volumetric flow rate, mass flow rate, and mass flow split. The latter option is primarily used for multiple outlet boundary patches where the user can specify the outflow as a fraction of the global inflow for each patch. A new porous pressure boundary condition has been added, which can be used for both inlet and outlet boundaries. The porous pressure condition calculates the pressure using the user-specified loss coefficients. The AIJ Richards Hoxie wind profile is a semi-empirical wind profile commonly used in the context of atmospheric boundary layer studies in CFD. In Helix version 4, we have an interface for it in our graphical user interface, and we have also added a new atmospheric boundary condition called turbulent spot method with anisotropic Vorton. In Helix version 4, a few enhancements were made in terms of wall functions. Wall functions are used to avoid resolving the boundary layer all the way down to the viscous sublayer. In the k-omega SST turbulence model, and Y plus insensitive wall function is used in theory for omega and turbulent production. And a zero Newman condition is used for K. The issue is that the inherited wall functions from OpenFOAM present strong variations in the computed shear stress depending on the Y plus value. To address the issue of Y plus insensitivity in shear stress computation within CFD and wall functions, a new boundary condition called NUT-U tabulated wall function has been introduced, which interpolates values from low Reynolds solutions to accurately compute U plus and Y plus, while mitigating discrepancies in traditional models. Also, by employing a modified Laplacian discretization, gradient errors in the viscous sublayer are minimized, accounting for omega's specific distribution and increasing the accuracy of the diffusion term in the omega equation. Lastly, the limiter in the code implementation of the k-omega SST model acts in all cells, but it should not be applied in the first near-wall cell, which is explicitly defined by the wall function, therefore being disabled in Helix version 4. The Darcy-Forchheimer porosity source now allows for the specification of a spatially varying multiplier that can be applied to the porosity coefficients. The porosity coefficients can also be specified as temperature dependent. A new thermal source was added where the user can specify a generic thermal source. Different specification options are available to the user, including fixed heat flux, fixed heat transfer coefficient, scaled heat transfer coefficient, and scaled source temperature. We have added support for the dual flow heat exchanger model, whereby a heat exchanger can be specified with two coupled regions, one representing the primary fluid and another the secondary fluid. Several methods for defining the heat transfer between the fluids are available, like the number of transfer units, commonly called the NTU model, the mass transfer coefficient, called UAL in our graphical user interface, and the heat exchanger effectiveness can also be specified by the user. We have added support for semi-implicit source terms for passive scalars and multi-species mixtures defined by the user. Users can set up sources either in absolute units or per units of volume. This source can be used to define a radiation source on a cell zone that accounts for both absorption and emission. To activate radiation sources, volumetric radiation should be enabled. A new vegetation source has been added, which can model the effects of trees on momentum, thermal, and humidity properties. Several options are available to the user for specifying the physical characteristics of the vegetation, such as the leaf area density, drag coefficient, and solar radiation absorption fractions, amongst others. Now let's have a closer look on what has been added in terms of solvers in Helix source code. As part of our significant efforts in refactoring Helix source code, we have consolidated the numerous solvers previously available in Helix, originally inherited from OpenFOAM. Many of these solvers shared similar functionality, with only slight variations for specific physics, leading to redundancy and reducing application flexibility. To address these issues and improve user experience, we have developed a more streamlined and unified approach to solvers, enhancing interoperability between different applications. We call this approach the Unified Solver Framework, in which flow models are added as solver objects in a modular fashion. In version 4, we have implemented the Universal Single-Phase Solver. Now, instead of having different solvers to account for heat transfer, buoyancy, transient effects, compressibility, and so on, this system comprises all the existent pressure-based single-phase solvers into one unique solver called Helix Solve. In terms of monitoring functions, we have added a new statistical quantities function object, which can be used to report on several statistically relevant values of an existing function object, such as mean, minimum, and maximum values, standard deviation, and others. The surface statistics function object computes the statistics of given fields from the selected surface objects, which can be patches, slices, or iso surfaces. Another monitoring function that was added was the effective choke area function, which reports on the effective area and backflow percentage for high-speed flows. We have also added the Kirchhoff-Fowlkes-Williams-Hawkins acoustic analogy to the noise propagation monitoring function object list. The Kirchhoff-Fowlkes-Williams-Hawkins acoustic analogy is a CFD model that predicts broadband noise from turbulent flows using a permeable integration surface surrounding the noise source region. It accounts for solid boundaries and moving sources, making it ideal for various broadband noise predictions. Now let's take a look at what has been added in terms of our View tab, the tab in our graphical user interface for post-processing your CFD simulations. A new field sampling function object has been added, which can be used to resample user-specified field datasets onto uniform grids. The resampled grid can be used with our runtime post-processing tool, and the file output is of PVD format. We have added the functionality to either slice or clip the domain using an external triangulated geometry file, which can be used, for instance, to monitor surface statistics at runtime. With respect to our runtime visualization tool, which has been introduced in past versions of Helix, we have performed a major refactoring of its library. There are great rendering improvements, and as you can notice in the graphs on the right, performance gains up to 10 times speed up in some cases. Finally, let's take a look at what has been added to our additional modules. First, in the context of the Unified Solver Framework, which I will call USF from now on, our adjoint-based shape and topology optimization is now rebuilt to be encapsulated inside USF. Adjoint solvers are solver objects that can be used together with the existing primal solver objects for the computation of sensitivity derivatives of one or more objective functions. The adjoint solver objects consist of adjoint flow solvers, geometric sources, geometric engines, and optimization controllers. For terminology clarity purposes, geometric sources represent the sensitivity derivatives that are computed based on geometric quantities, like volume, curvature, etc., and do not require the solution of a primal or adjoint flow solver. Geometric engines are the solver objects to represent the shape or topology parameterizations and manipulation of geometry, like the level set porosity and propagating front modifiers for topology and node-based, lattice-based, and so on for shape modifiers. Lastly, the optimization controller is a special solver object that controls the optimization process, which should be used if a geometric engine exists. With respect to our Helix coupled additional module, we have available a compressible pressure velocity coupled solver plus other solvers in segregated algorithm like energy solver, passive scalar solvers, and so on. The coupled solver in this new version is completely USF compatible, accounting for physics such as compressible and incompressible flows, buoyancy flows, radiation, and etc. Density-based solvers are also available. The coupled solver in Helix version 4 has the usual strong pressure velocity coupling algorithm. It accounts for all Mach numbers and provides a speed up to 10 times in solution time. Our Helix Marine additional module, specific developed for ship design for the naval industry, has new 6 degrees of freedom library coupled to our adaptive mesh refinement tool for more efficient mesh generation for simulations with moving parts. This new library is ideal for calm, water resistance, and seakeeping analysis, and it's suitable for both displacement and planning hulls. So I hope you all enjoyed and found this webinar useful, in which we have presented the new features and enhancements of Helix version 4, which was released in April 2023. As a summary, Helix v4 source code has a completely new system based on what we have called the Unified Solver Framework, which focus on the consolidation and generalization of our code, better usability, and enhanced modeling features for our customers. The next version will be Helix version 4.1 due to autumn 2023. We expect our customers to benefit a lot from this new chapter of our software roadmap. For any questions, you can send an email to info@enggys.com and we will be happy to talk with you about your CFD requirements if you are interested. Thank you very much for your attention.